Okay. I think it's on. Okay. So I guess we finished a lot of stuff on linear programming. So I covered simplex, ellipsoid, interior point. Now I want to sort of transition into other stuff. So it turns out the thing I'm going to cover today can also be applied for linear programming, and I'll show you that, but it's more than just a tool to solve linear programs. And then once we're done with this, you're just not really going to see solving linear programs anymore. Okay. Okay, good. So today what you're going to see is kind of multiplicative weights. So today. I'm just curious, has anyone seen multiplicative weights before? Okay. Okay, so, or rather I should say, how to know how to choose, which expert advice to listen to. Right, so for example, you like to trade stocks. There are lots of self-proclaimed experts who tell you what to buy so that you make money, and you're not sure which one you listen to. So you want to you want some strategy for deciding which one to listen to. Okay, and what I'm going to say is going to remind you of competitive analysis. Well, actually, first let's just look at competitive analysis. So let's first, before we get into multiplicative weights, let me just go into this listening to expert advice. So the setup. Okay, is that there are T days and N experts. Okay. Each day, each expert will say yes or no. Okay, so for example, will it rain today? Will this stock go up in value today? Okay, they're each going to tell you what they think. And then you have to decide what you think the reality is and then make a decision. Okay, so we have to, we have access to all these expert opinions. Okay, and we have to make a decision. Right, and what we want that at the end of the T days, the number of mistakes we've made is small. So, we want to be able to, of course, we want some provable guarantee on how small a number of mistakes is. But, this is kind of a, if you don't define your measure of success appropriately, this is a hopeless problem, right? Because it might just be the case that none of the experts know anything. They're just saying random junk. And then you're going to say something, and then reality can hit you and say, oh, actually, it's the opposite of what you said, right? I mean, no one knows the future, so what are you going to do here? So, what's the kind of, I guess I may have spilled the beans already. In such situations, what do you usually want to measure success as? Or, what's something that we've covered before that seems like a good way to maybe measure success? Yeah, sure. Competitive analysis, right? So one thought. Be competitive with the best expert in hindsight. Right, so at the end of the T days, you're going to look back and you're going to look at each expert and see how many mistakes that expert made. And you want to make sure that you're not much worse than the best of them. Okay. So what's one natural, oh yeah?
So at any time step, you know if the experts were right or wrong at the previous time steps, right?
Yeah, so you have infinite memory. You can remember everything every expert has ever told you. And at the end of the day, you see what actually happened. You see whether or not it rained, for example. Yeah. Okay, so I mean, what's the simplest thing you can imagine doing in this model? Yeah.
We can see the score for each expert so far, and see the percentage of correctness.
Yeah.
At each step, we take the expert that has the highest percentage of correctness.
Be even simpler. I mean, let's not even look at histories. So I pull all the experts. They all tell me something. Yeah, just vote. Like take a majority vote, right? So, one simple algorithm. Yeah, we are gonna over the lecture we are gonna see how to get more complicated in terms of taking the history into account. But first let me just start off with something really simple. So simple algorithm. Just take a majority vote. Okay, and then claim if there exists an expert I. Well, let me say if there exists an expert that never makes a mistake, okay, I want to make one modification to this simple algorithm. So we're going to take a majority vote. I'm going to take history into account in a very minor way. I take the majority vote, and if anyone is wrong, at the end of the day, if I realize someone was wrong that day, I just kill them, okay, or I stop listening to them. Okay, I take a majority vote. At the end of the day, kill all wrong experts. Okay, so the claim is that if there exists a perfect expert, then we make at most how many mistakes? Sorry? Oh, yeah, wait, I heard something. I heard log n, though, is what I thought I heard. That's why is. Okay, so it's log n. We make at most log n mistakes. Or maybe I heard CL log n. Okay, that's okay, right? So the proof. Well, good. So the point is, every time we make a mistake, most of the people were wrong, so we kill half the people. Okay, so right, so every day we make a mistake, we kill half the people, at least half of the population of the experts. So that right, and we always have one person alive, namely the perfect expert. So the number of killings we can do is at most log wrong days. Okay, but that's assuming there's a perfect expert, right? So normally in competitive analysis, I just want to say I'm competitive with the best expert, the one who had the fewest mistakes, right? So unfortunately, this algorithm, you can't just analyze this algorithm in that model, because it could just happen that on day one everybody was wrong, and then you killed everybody. Now who do you listen to from then on, right? So what's a modification of this algorithm if you want to be competitive against the best expert? kill the worst half. I mean, let's say day 1 everybody's wrong. What do you do day 1? And then maybe the best expert is right from day 2 onward, right? But now you don't know because you killed him. I mean, he's not really dead, right? He's we're just ignoring him. So he's not really. Yeah, you can go back to him. But yeah, so what do you do? Hmm? Kill at least half randomly. Yeah, I'd have to think about. I don't know off the top of my head what that would do. But let me suggest, lead you toward a different algorithm. So what's the problem with this algorithm? It's what I just said, right? It's that everybody could be dead. So one thing you could do is, if you're ever in a situation where everybody is dead, you just revive everyone. Okay. So do as before. I don't know. Yeah. Sorry, I just thought. I don't know if people watch Naruto. This Edo Tensei. No. Okay, never mind. So do as before, but if everyone is dead, then revive everyone. And the claim, if the best expert makes E errors, then we make at most E plus 1 I think log base 2 of n errors. Okay. Do people believe this? Why do you believe that? Yeah.
We kill the best expert E times every time he makes an error in the worst case, and all the other experts we make log n things.
Wait. So we kill the best guy. We kill him at most E times. You said. Okay.
He happens to be revived every time he makes an error.
Right.
We kill him off, and
Right.
then we make at most that many mistakes before we kill everybody else if the experts are wrong.
Right. Yeah. Exactly. Right. So. Right, so the number of phases, like revival phases, is E plus 1, including the first phase when we just start. Right, and then basically within that phase, we make at most we can make at most log n errors before we kill everybody. Okay, so phase ends when we kill the best expert. That's not really legible. When we kill the best expert. And at most log base 2 of n errors per phase. Okay, good. Okay, so that's, it's something, but it's like a logarithmic competitive ratio, right? So, well, I mean, there's also this additive 1, but if you ignore the additive 1, it's roughly a log n competitive ratio. So, I want to do something better. And the question is, how can we do something better? And the way we're going to do something better is we're going to allow for some additive error in the competitive ratio as well. Okay, so Okay. So I'm going to find some notation. Let MT equal number of our mistakes by the beginning of day t, and mi, little mi t, is the number of expert i's mistakes by the beginning of day t. Okay. So I'm going to show you we can get, there is a strategy, there is an algorithm which allows us to get MT to be at most something like 2 times 1 plus epsilon, the min over I from 1 to n, basically the best expert. Is this legible? 1 less than or equal to I less than or equal to t of mi. This is, let's say, t plus 1. Let's say by the end of day t. Plus 2 ln n over epsilon for any epsilon in the range from 0 to a half. Okay. So on the one hand, right, before we basically had, so this is like E. Before we had roughly log n times E. Now we have roughly 2 times E. But then there's some additive error depending on how close we want to be to 2, as well as depending on this log n. Anyway, we already had an additive log n. So that's not so bad, right? Okay. Any questions? Okay, so what's a natural thing to try? I know at a very high level, right? So what's the thing we did here is pretty extreme, right? Which is once you're wrong ever, you're just dead, right? Okay. So okay, good. So yeah, what's something you can do that's a little less extreme than just killing people when they make a single mistake? Yeah, trust them according to their past performance, right? So here we said that we're taking a majority vote, right? Majority vote usually means everybody has an equal vote. So we could weigh people's votes according to how much we trust them, right? And if someone's been making mistakes a lot, we should trust them less. But we'll still count them, just not as much, okay? So the idea is, never kill an expert just for being wrong. Just trust them less. Okay, so we're going to have a weight vector, W, which starts off as the all ones vector of dimension n. So, okay, so this is like the weight in the majority. And we will take a majority vote, a weighted majority vote. Where expert I is weighted by Wi. Okay. Okay, great. So we can still be wrong. Now what are we going to do when we're wrong? So there are some experts here who we trust less now because they made a mistake, and we're going to decrease their weights. At the end of the day, for each wrong expert I, we're going to set Wi to be 1 minus epsilon times Wi. Okay. I mean, we sort of implicitly are, just because you could say I'll decrease him by 1 minus epsilon and increase the others by 1 plus epsilon, but really that's the same thing as saying I'm increasing the other guys by the ratio 1 plus epsilon over 1 minus epsilon, and I'm not changing them, right? So yeah, without loss of generality, you can assume that you'll either increase the correct people and leave the others the same, or decrease the incorrect people and leave the others the same. Yeah. Okay. So this is the algorithm that I claim is going to get this bound. Okay. Good. So let's prove it. So actually, what I want to do is let me introduce some new notation. So let's say Wt is the weight vector at time t, or on day t, at the beginning of day t. And I'm going to define a potential function. Phi of t is going to be the sum over all I from 1 to n, the sum over all experts of their weights. So in particular, on day 1, the potential is n. Okay. Now, what can we say about phi t plus 1 versus phi t on days when we make a mistake? Right. Yeah.
Phi t plus 1 decreases by n by 2. Wait, say.
N epsilon by 2. Oh, sorry. So let me write down. I just want to write down an inequality. So you're saying phi t plus 1, and what's the inequality? Actually, I want to upper bound it. Or yeah, I want to upper bound it. So is there an upper bound you had in mind?
Right. It's at most like phi t minus n epsilon by 2, right? Because at least half the expert.
You said.
Oh, sorry, with weights.
Right. So I mean, I want to say, so for us, I guess what I want to say is, so the weighted majority is wrong, which means at least half of this weight has to be on the wrong thing, right? So what I want to say is, if you look at that half of the weight, that half of the weight decreased, right? By 1 minus epsilon. And the other half of the weight, I don't know. I mean, they could have been wrong too. But I'm saying at least half was wrong. And the other half, it definitely didn't go up. It definitely didn't go up. So I can just say that that's just, let's say it stayed the same as an upper bound. Right? Which is equal to 1 minus epsilon over 2 times phi of t. So now you can do an induction, and you can bound phi of t plus. Okay, so first of all, what do I want to say? This implies, by induction, that phi of t plus 1 is at most the original phi times 1 minus epsilon over 2 times the number of mistakes that we make by time capital T. Right? Which is equal to, this is just n. Okay, and for what I'm going to do next, I also want to use the fact that 1 minus x is at most e to the minus x. 1 plus x is at most e to the x. So x is negative epsilon over 2. So this is at most n times e to the minus epsilon mt over 2. Okay, good. So this potential function is just going to serve as something that lets us get a bound, right? So we've now upper bounded the potential. Now I want to lower bound the potential. And I'm going to use kind of the weakest lower bound you can imagine. So say I is some expert. In particular, maybe I is the best expert. What can you tell me about phi t plus 1 compared to the weight of the best expert, compared to the weight of the ith expert? We have phi t plus 1. I want to say is at least something. Okay. Well, it's the sum of all the weights. And all these weights are non-negative. So it's at least wi of t. But what is wi of t? Yeah, it's 1 minus epsilon to the number of mistakes of the ith expert by time t. Okay. So actually, did I even want to do that exponential? Maybe not. But so now I want to do one thing. I want to say this implies altogether that this, therefore, is at most that upper bound. So this implies that 1 minus epsilon to the mi of t is at most, and actually let me just stick with this one, n times 1 minus epsilon over 2 times mt. Okay. And now I'm going to take ln of both sides. Then I get mi of t times the ln of 1 minus epsilon is at most m of t ln of 1 minus epsilon over 2 plus ln n. Okay. Now, let's just remember a very small amount of calculus. Okay, so calculus tells us that if you Taylor expand some function, right? So f of x around say a, so f of a plus f prime of a times x plus, and let's say you do it up to the linear term and you want to understand what the error is. The error is the second derivative at some point z over 2 times x squared for some z in the range from a to x, or x to a, depending on which one's bigger.
That should be x minus a squared.
Yeah, thanks. Whoops. Okay. So this tells us, this implies that ln of 1 minus epsilon, right, or ln of, say, 1 minus x is equal to minus x plus an error term, which is the largest derivative of, so you take the function ln of 1 minus z. Okay, so times x squared. So here I'm Taylor expanding about 0. And f of x is this ln of 1 minus x. Actually, f of x is ln of 1 plus x. And then this is f prime of some z for z in the range from, let's say, 0 to a half. Okay. So you can show that if you just bound the largest derivative of this function, ln of 1 minus x, in this range, then you can show that this thing, well, certainly, you can show that this thing is certainly going to be non-positive, okay? And it's going to be at least, what's the worst case? So, I'm sorry? Yeah, I think you can say that, you can show for x in the range from 0 to a half, ln of 1 minus x is certainly at most minus x, and it's at least, minus x squared or something like that. Yeah. Basically just for this Taylor's theorem reason. Okay, so now you go back to here, and you say, well, this m of t ln of 1 minus epsilon over 2 plus ln n, well, ln of 1 minus epsilon over 2 is at most negative epsilon over 2. Yeah, I guess I could have just taken the ln over there. But then for the other side, then you need to use this fact. And then on the other hand, you have this is at least, what we said, mi of t ln of 1 minus epsilon, which we said was at least mi of t, well, negative epsilon minus epsilon squared over 2. Mi of t. Okay, and then now you multiply by the negative sign, you rearrange things, and you get the theorem. Okay, so that's it. Okay. So are there questions about the algorithm or anything about its analysis? Okay. So now I want to go even further. I want to make some generalizations. Some, let's say, generalizations to the model. Okay. So, first of all, let's say at each step, we want not, let's say, not to not make a mistake, not to be correct, but to minimize the, let's say, the probability that we're incorrect. Okay. So what I mean by that, I mean in every day we're not going to choose an expert to listen to. We're going to come up with a probability distribution over experts, i.e., on each day we output probability distribution PT over the experts. Okay. So we want sum from t going from 1 to capital T of the dot product, let's say mi of t dotted with pt. We want this to be small. So that's our expected. This is the probability that we make an error. So imagine that mi is 0 if we're right and 1 if we're wrong. Okay. Also, we will assume that MIT, so before we said that it's either 0 or 1, right? The person was either right or wrong. Now we're going to assume that this is actually in the interval from -1 to 1. Oh, yes. Oh, good point. Whoops. Okay. So, yeah, this is MT is now the mistake vector at time t. So, mi, so let me write this over here. So I'm imagining now that mi of t is equal to 1 if expert I is wrong at time t, and 0 otherwise if he's right at time t. Yeah, so it's no longer the number of mistakes by time t. Yeah, sorry, I should have used a different letter before. Now this is a kind of, okay. also will generalize to, instead of just saying it's binary, we'll say that MT, this vector MT, is actually in minus 1, 1 to the n, and not just 0, 1 to the n. Okay. Very good. So you should think of a negative number as meaning, as being like a benefit, right? So we're trying to make sure that this thing is small. So negative numbers help us. So it's like not only was he right, but he was right and gave us $100 or something. Okay. So the multiplicative weights algorithm right. So we need to figure out what this probability vector is that we're going to output it on day t plus 1. We're going to say that p t plus 1 sub I is equal to, okay, 1 minus epsilon mi of t. Pi of t. Okay. And so this is just a generalization of what we already saw, right? Before, mi was either 0 or 1. If it was 0, then we didn't change this. Think of now this p as being the weight vector. Okay. Before, if mi was 0, this was just 1, so we didn't change the weight at all. And if mi was 1, meaning they made a mistake, then we decreased the weight by a factor of 1 minus epsilon. Okay. So now we can also increase weights because of the fact that mi can be negative. But you could also imagine, that's just ease of notation. Okay. You could also imagine not actually doing that and just keeping the ratios similar. Okay, so so this algorithm, so I'm going to keep calling it the multiplicative weights MW algorithm. So MW has been rediscovered over and over again by different people with different names in different fields even. So like economics, theoretical computer science. When I say that, I mean, like algorithms, let's say. Machine learning, etc. Okay, I'm not going to put all the references, but there's a book or monograph that goes into the history and also talks a lot about various applications of multiplicative weights. So you can see a book, by Aurora Hazan. Kala. Actually, this is the monograph right here. So what year is that? 2012. Okay, so, yeah. I'm sorry? This? A. So again, we want to be competitive with the best expert. Before I start, proving things, you got a question? Yeah, that's. Yeah. So really what I maybe should have said is, I want it to also even be consistent with last time. And then I'll say pi of t is just the weight over the sum of all weights. Yeah. Okay. So theorem. Now I want to say that multiplicative weights does well compared to the best person in hindsight. So what I'm going to say here is that the sum from t goes from little 1 to capital T of this dot product, mi of t dotted with pi of t, where p is the thing that multiplicative weights outputs, is at most this should be m of t. This should be pt. There's no I. Right, there's no I here. M is a vector indexed by I. Okay, so this sum of expected costs should be at most the sum t goes from 1 to capital T of the number of mistakes of person I. And then what we're also going to get is plus epsilon times the sum over t of the absolute value of mi of t plus ln n over epsilon. Okay. Questions about the statement of it? No. So let's just start proving it. So proof. Right. So again, we have this potential that I again set over there. So remember, phi of t is the sum over I from 1 to n of WTI. Right, and again we can say the same thing as last time, right? So I want to upper bound phi and also lower bound phi, and then I want to compare those two things, and then derive some inequality involving how we do versus how expert I does. Okay. Okay. So let's see how these things relate. So phi of t plus 1 is equal to, by definition, the sum I from 1 to n of wi t plus 1. And then now we're just going to plug in the definition. Okay, so this is equal to the sum over I of wit times 1 minus epsilon mi of t, right? Which is equal to, if I distribute this, the sum of wits is just phi t. And then here I have the sum of, what is going on here? This is epsilon. So here this is just phi of t minus the sum over I wi of t times mi of t. Okay. But what's wi of t? Right? By definition, relating it to p, this is just equal to pi of t times phi of t, right? So this thing here, oh yeah, there's an epsilon. So this thing here is equal to phi of t times 1 minus epsilon basically mt dotted with pt. Okay, good. And now I'm going to use again my favorite trick. This is at most phi of t times e to the minus epsilon m of t dotted p of t. So by induction, this implies that phi of t plus 1 is at most phi of 1, which is n, times e to the minus epsilon sum over t from 1 to t, mt dotted with pt. Yeah. Okay, good. And then now again we do the other side. And we're going to say also phi t plus 1 is at least wi wit, right? Which is equal to, what's wit? Right, that's right. So this is equal to pi of t times, well, so let me just write it in terms of, yeah, so that's true. But yeah, so not expressing in terms of p, but just in terms of kind of, basically in terms of that. So let me write, so I want to say what you get by induction, basically. Okay, so this is equal to 1 minus epsilon. So basically the product t going from 1 to t of 1 minus epsilon MIT. Right. Let me make sure I'm... Okay. Very good. And then now I want to use some calculus yet again.
Sorry, should it be a t plus 1,
Oh, yes. Yeah. Okay. Okay, and this thing is at least, let me write this, 1 minus epsilon times the sum over, let's say, the less, at least zeros mi of t times the product of 1 plus epsilon, sum of less than 0 mi of t, where sum of greater than or equal to 0 is over the I such that mi of t is bigger than or equal to 0. Sum over the t. Okay. And where does this come from? This again is some more calculus tricks, basically. So I'm not going to actually do it. So calculus claims. Let me make sure I write it down properly. So 1 minus epsilon to the x is at most 1 minus epsilon to the epsilon x if x is in 0, 1. And then also 1 plus epsilon to the minus x is at least, or at most 1 minus epsilon x. If x is in minus 1, 0. Okay, so the way that you would prove these actually, the way I just realized the way I did it with Taylor's theorem is a little clumsy. You can just use the fact that, for example, so e.g. the first bullet, you just use the fact that the function f of x, which is 1 minus epsilon to the x, is a convex function, right? You just check its second derivative and it's positive. So that implies that, f of x, which is f of 1 minus x times 0 plus x times 1, should be at most 1 minus x times f of 0 plus x times f of 1. Right? That's what it means to be a convex function. And then that's exactly that. Okay, so you can verify these things. And here I'm just applying that to, right? So this is my x. This is my 1 minus epsilon x. Okay. And then I separate it into cases. Either this thing I'm adding is positive or negative depending on the sign of mi of t. So this is the cases when mi of t is positive or non-negative, and this is the case when mi of t is negative. Okay. So now you just put things together. You say, well, phi of t plus 1 is at most this quantity, and also phi of t plus 1 is at least this quantity. So this implies that 1 minus epsilon sum t, sum bigger than or equal to 0, mi of t, times 1 plus epsilon, sum of less than 0, mi of t, is at most n times e to the minus epsilon, sum over t from 1 to capital T, of mt dotted with pt. And then you just take lns and then rearrange things. And okay, so so if you really want to see that calculation, I mean, there's really nothing more going on after this. You can look at the paper yourself. Okay, so it'll be in the notes. Questions? So now, what I want to finish, and this will probably carry on into the beginning of next lecture as well, is I mentioned that this multiplicative weights thing is not only about the stock market and weather. You can also use it to solve linear programs, or approximately solve linear programs. Okay, so Plotkin, Schmoyes, Tardish, say math operations research. So use multiplicative weights to approximately solve. Packing covering LPs. Okay, so remember I defined packing covering LPs when we're doing, I guess, competitive analysis at some point. Don't worry though, when it comes time, I will remind you. So now, we'll show how to use MW, just for general LPs. Assuming that you have a certain kind of oracle that I will describe. Okay, so this description is in that book as well, in that monograph by Aurora, Hazan, and Kale. So setup. Okay. Is that we I want to check if AX is at least B and X is in some set P is feasible, where P is a subset of Rn, is convex. Just remember, it just means that if you take a convex combination of points, that stays inside of P. Okay. And A is an m by n matrix. Okay. Now, if not feasible, we should say so. Otherwise, we should find an x such that x is in P and ax is at least b minus epsilon times the all ones vector. Okay. Right, so we want ai dot x to be at least bi. So what I'm saying, ai dot x should be at least bi minus epsilon for all I. Okay. So we're going to see that multiplicative weights, assuming some other property of the set P. I mean, I didn't say anything about P, but assuming that P allows you to do some things efficiently, multiplicative weights will allow you to find such an x quickly. By quickly, I mean in a small number of days. Okay, so this capital T is, so there are no more days anymore, but yeah.
Is epsilon small enough? Can you later round it to a real vertex?
Yes, so yeah, that's a good point. So I think we said before, you know, once you solve things up to really fine precision, like there was this L parameter before, right? Then you basically solve the problem exactly. The problem is that in order to get this kind of guarantee in multiplicative weights, the number of iterations you'll need to do the updates, meaning this capital T parameter, is going to end up being something that's polynomial in 1 over epsilon, right? Whereas with interior point, we were getting away with something that was like log of 1 over epsilon. Yeah, so yeah, it would just be extremely slow is the problem. Okay, any other questions? Yeah, actually, I should, so yeah, that epsilon should really be like exponentially small in L. That's the point. Okay. Okay, so let me just give an example before we actually talk about how to use this, how to use multiplicative weights to solve this. So example, let's say fractional set cover. So let L, I don't want to use L, let's say, let's see alpha. Let alpha in R be such that alpha is at least opt. Then we're going to set P to be, well, first of all, let's write the LP down. So we want to minimize the sum over all sets S of XS such that for all elements E, the sum over all sets containing E of XS should be at least 1, and XS should be at least 0 for all S. Right, so we have a set of elements we want to cover, and we have a collection of sets S. Okay. So in the integral program, you imagine each XS would either be 0 or 1, telling you whether or not you took the set. But here we relax it to a linear constraint. Right, so as I described it here, there's no optimization. There's no minimize of linear forms. This is just a feasibility question, right? So the way you would use it for a problem like this is you would assume that you know an alpha such that alpha is at least opt. And then you would set P. I mean, I didn't tell you what you really need from P, but you would set P as the set of x's such that, let's say x is at least 0, and sum over s xs is at most alpha. Okay. So you don't actually know opt, right? So, what would you do? Suppose that you had a way of deciding now the feasibility question. Now you want to figure out if, let's say, these constraints, if the star constraints subject to x being in P is feasible. So that's the way we're actually going to use multiplicative weights. But you don't actually know this alpha, right? So, what would you do? Suppose you had a way of deciding feasibility of this. What would you do to actually to figure out the optimal value now for? Yeah, binary search, right? So binary search on alpha. Right, and alpha is anything between, let's say, 1 and the number of sets. So this is the number of sets in your collection. So you could binary search. And then at the end of the day, what would you get? If it were feasible, you would be off by this epsilon, right? If feasible, you would get x such that for all e, the sum of xs is at least 1 minus epsilon. Right, so I don't know, so if people recall, one way to get an approximation algorithm for set cover is to solve the LP relaxation and then do some randomized rounding of sets and choose them according to the probabilities x of s. Okay. So that's one reason you might want to solve this LP, to then feed it into that randomized rounding algorithm to approximate the actual integral set cover. But the problem is this is not a feasible solution for the relaxation. Right? So what would you do to make it a feasible solution? Yeah, you just rescale, right? So final solution not feasible, perhaps, right? But x over 1 minus epsilon is feasible. And it achieves cost well, the cost is this dot product. Well, the cost is this sum, the sum of the xs's. And before, it was in P, right? So we knew it was the most alpha. It achieves cost sum over xs at most over 1 minus epsilon is at most alpha over 1 minus epsilon, which is equal to 1 plus O of epsilon times alpha. So you're getting an approximation algorithm anyway. You're getting a ln n approximation. And now if you use multiplicative weights to solve the LP, you would get a ln n times 1 plus epsilon approximation. Right? And the point is you wouldn't have to run. So we'll see what you actually need to do in the multiplicative weights algorithm to get this x vector here. But the point is that it's going to be a fast algorithm. Okay, it's not going to be as slow as ellipsoid or interior point, etc. Okay. So are there other questions? So this is the end of that set cover application. So now let me get to the analogy. Okay. So I'm going to set, so given some x, we'll define mi to be the cost vector, to be ai dot x minus bi. Okay, where wait a second, what do I want to say? I want this to be in minus 1, 1. So okay. So let me think. I guess I'll get into this normalization next time. I confused myself about. I want this to be in the interval from minus 1 to 1. But the point is, so this is going to be some positive or negative number. So if it's positive, that means the constraint is actually satisfied, right? So each constraint, i.e. row of A, is an expert. Okay. And so it looks weird because positive MIs were supposed to correspond to mistakes, whereas here a positive MI means we're actually satisfying this constraint, right? But the point is you should think of the experts as telling you whether or not they think constraint I is hard. Okay? I think that's the right way to think about it. So then if it's positive, then you've satisfied the constraint. So it's not really that hard. Okay? And the more you've satisfied it, the bigger the slack is, then the easier it is, which means the more wrong that expert was. Okay? But really what matters more is think about how multiplicative weights treats experts who are wrong. It weights them less, right? So multiplicative weights is trying to figure out, so eventually, we want this approximate feasibility up to this epsilon over there, right? Eventually we want approximate feasibility. So multiplicative weights, wants to focus all its weight on constraints that are not yet satisfied. Right? So the point is, if something is very well satisfied, we're going to spend less effort on it from now, in the future days, the future iterations. Whereas if it's already satisfied, if it's not satisfied, then we're going to pay more attention to it. So yeah. So I guess next time, it's now 4. Next time I'll actually give you an analysis to show you the number of iterations you need on multiplicative weights to get this kind of approximate feasibility guarantee, and also what property do you need from P, et cetera. Okay. So that's Thursday. And I guess that should not take too much of the lecture, and then we'll start something new too. No more solving LPs at all.